Welcome everyone to Women Who Code San Francisco mock interview with the Ellas, Gabriela and myself, Daniella.
Hi,
The Women Who
Daniela.
Code. Hi, Gabriela. How are you?
Very, very good and excited to be doing this mock interview with you. Thank you.
Me too. Me too. So the Women Who Code San Francisco group has been working on trees and graphs the past couple of weeks, and to conclude that study session, we are here conducting a mock interview. So here's our little mascot here at Ella. Now, for today's mock interview, we're going to be solving two problems. And during the first round, Gabriela will be the interviewer and I will be the interviewee. And we will switch roles for the second problem, where I will be the interviewer and Gabriela will be the interviewee. We will also be trying two different whiteboards. So when I solve the problem, the first one, I will be trying the Google Jamboard, and Gabriela will be using Google Drawings. It's just trying different ways to whiteboard solutions. So with that, I am going to turn this over to Gabriela to conduct the first part of our mock interview. So Gabriela, turning control over to you. Take it away.
Thank you, Daniela. So I'm going to start sharing my screen. Could you please stop your sharing and then I can start mine. Thank you. And we're going to just get ready with the problems and let's get this starting. Please let me know if you can see the document in your computer or in your screen.
Yes, I can.
Perfect. So this is the first problem, and I'm going to be reading the problem so we can read it together and you can ask questions during the reading also. So this one is diameter of a binary tree. And this is a lead code 543. So it says, given the root of a binary tree, return the length of the diameter of the tree. The diameter of a binary tree is the length of the longest path between any two nodes in a tree. This path may or may not pass through the root. The length of the path between two nodes is represented by the number of edges between them. And here is an example of a tree. We can let's finish up reading the problem. I'm going to open the lead code page so we can go over also the restrictions and the conditions of the problem. And this example, it's showing a tree with 5 nodes. So you can see that this is a binary tree which is not balanced, and it has 3 nodes in the left subtree and 1 node in the right subtree. And the output of this problem after the solution, it's 3, which is the length of the path, the longest path, which is going to from the node number 4, then number 2, 1, and 3. And this is the diameter of this tree. And then the example is just having 2 nodes, 1 and 2. It's just 1 node, I mean 1 path, and the output is 1. So the constraints are the number of nodes in the tree is in the range of 1 to 10 at the power of 4. And the node value can be between 100 and 100 negative. And those are the constraints for this problem. Do you have any question about the problem?
So when you say the diameter of the binary tree, well, can I share my screen?
Yeah.
Okay, 1 second, if you can stop
share it.
sharing yours.
you can start sharing.
Okay. Okay. Mhm. All right, here we go. I'm going to share this. And here we are. Okay. So, yeah, there we go. Diameter of a binary tree. Okay, so it's the longest path between any two nodes in a tree. So this path may or may not pass through the root. So in this case, the path is passing through the root. I also want to go over the cases where the path may not pass through the root. So could I use like a Jamboard to just go over that?
Yeah, please. You can use whatever you want to
All right.
explain the solution that you think of.
So what about if we had something like this? And so something like this, 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 and this. And so we have these nodes. 1, 2, 3, 4, 5, 6, 7, and 8. Okay. So in this case, and again, you mentioned that the diameter of a binary tree is the length of the longest path between any two nodes. Okay. So in this case, we have this one path, right? Over here. So here we have 1, 2, 3, 4, 5. So here the diameter is 5. And here, well, I could also actually add one more here. So in this case, my diameter is going to be 1, 2, 3, 4, 5, 6. So for this path, it is passing through this particular node, where this node is the root node. But relative to its parent, for this node here, it can for this node here, it's going to do something similar. It's going to get the maximum path from its left subtree, the maximum path from its right subtree. So here, the maximum path from its right subtree, it could either be this path, or we could pass along this path. It just so happens that they're both the same. So this would actually return 3 and then plus 1. So we get 4 here, and 4 plus 1 is 5. So here the diameter is actually the diameter of this tree with this as the root. But passing through here, this diameter is 5, but here this is actually 6. So here the answer would actually be 6. And so this is a case where it's not passing through the root, correct? Okay. So, well, as I'm looking through this problem, I see that at each node, we have to calculate. We can calculate the diameter of the tree with that node as its root. So that's one thing we can actually do. And at the same time, we can also basically return to its parent um, the maximum uh, the maximum path, right? The longest path that is passing through this node to its parent, because we want to kind of we want to optimize and get the maximum length, the longest length from a leaf node to to the parent. So the since this is a tree, um, I can, and this is a binary tree, so I would think of actually traversing this tree in the kind of traversal that I would be thinking of is I'm thinking of is a depth first search, because I want to get to the longest length. So I want to traverse all the way, deep down that particular tree. So I'm thinking of doing like a DFS. And since the decision, or the computation of the diameter at a specific node is made after its left subtree and its right subtree have been processed, I'd like to do like a post-order traversal. So that's what I'm thinking of doing, like a post-order traversal. And so whenever my left and my right tree have been processed, and I'm now back at my root node, I can compute two things. I can calculate like the local, what is I can this the local sum here, okay? Or you could it would just be equal to, the maximum path return from my left subtree plus the maximum path return from my right subtree. That would give me my local sum. And then as far as what I have to return to my parent goes, I would say I would choose the longer of these two paths, and then I would actually return one to my parent. So that's kind of what the algorithm I have in mind. And I would keep track of the maximum diameter so far. So that's what we have here.
Could you explain a little bit about why do you think that it's in this case the post-order traversal is the best option for this kind of problem?
Sure. So in this problem, we want to find out the longest path between any two nodes in the tree. Now, to get the longest path, we would do best if we start at one leaf node and end with another leaf node. And so what that means is we have to traverse all the way down to a leaf node, correct? And then so in this case, for example, with this subtree here, with the root as 2, I would traverse all the way down to the leftmost nodes, which is like 4, and then kind of go back and then get traverse also back to this particular to this other child, and that's how I can get the maximum length. So likewise with 1, I want to traverse all the way down my left subtree. I want to traverse all the way down my right subtree, and then at each point I'll be computing what's the basically the diameter at that node. I'll be computing that. And so the goal is to compute the diameter at each node, and then calculate the maximum diameter. But basically, if you want to get the longest path, we need to get to the leaves first. So that's basically why I want to do the depth first search. And we need to compute the values at the leaves first, and because because then only once we have computed that, we can use those values to compute the diameter at the root. So that's basically why.
Okay. You can continue. Thank you.
Okay. So there are two options here. One, we can actually solve this problem recursively. So the recursive solution is like, you know, just the brute force solution. So uh, in the recursive solution, basically the time complexity for the post order traversal is going to be O(n), because we're going to be traversing all the nodes, and the space complexity is going to be OH, because this will be a depth first search, and the where the height H is the height of the tree, and the height, it will be, if it were a balanced tree, for example, let's say it was just 1 2 3 like this, then the height of the tree would be like O log n. But if it was skewed, for example, if he just had nodes 1 2 4, then the space complexity would be O of n. So that's the recursive solution. And then there's also the iterative solution, where the iterative solution is there a certain, I would prefer to do the iterative solution, because in Python, the Python interpreter has a limit for the recursion depth. And if you exceed that limit, then you will actually get a recursion error exception. So that's just something I would prefer to use an iterative solution to compute the diameter.
Yeah, I see what you mean about the comparing the iterative solution versus the recursive one.
Mhm.
And I think that's a very important point when you want to think about how many resources do you want to use in your solution. So that's a good point that
Mhm.
it's good to mention.
Mhm.
So for this case, you want to use the recursive technique, or you want to use an iterative solution.
I could use either. Is there um, in the interest of time, I mean, I could do either actually. But I think I mean, I would prefer to do iterative, because it just seems to be it's a cleaner approach, and avoids the issues with Python and just the
The
recursion
memory.
limit. Mhm.
Hmm. Very good. Okay, sounds very good.
Okay. Okay. Sounds all right. So that's fine. I will start coding. So we're going to be I'll be putting just a few comments here. So we're going to do a post order, and then we're going to do an iterative traversal of the tree. Okay. So this is diameter of a binary tree. So the diameter of the binary tree is the length of the longest path. So we have to keep track of this what is the longest path? And the longest path initially, I'm just going to initialize it to something. Okay. All right. And then the length of a path between two nodes is represented by the number of edges between them. Okay. So since we're going to be doing the iterative approach, what I would like to use is, I'm going to use a stack, because I have to simulate the function called stack. So I'm just going to call this stack, I'm going to call it a post order stack. And I'll call it so post order. So I'm going to use the list, okay? And I'm going to actually use a tuple. And the reason I want to use the tuple is because I need to process a, a node only after its right subtree has been processed. So what I'm going to do is, initially, I'm just going to add this one tuple, which is root. And the second value here of the tuple is basically just telling me, has my right subtree been processed? And initially, it's going to be false. Okay. And now I'm going to just walk through this particular, this is basically my stack. Okay. All right. So here's the first, so this is just the, I'm going to just do the iterative approach. So here we have, I'm going to node, and I'm going to say write subtree has been processed. And I'm going to do post order dot pop. So the first thing I'm going to say is if node, right? If, because this is a class 3 node. If node, and if my write underscore subtree was processed, then I need to do a couple of things. First, I need to get the value from the from my write subtree, that what my write subtree has returned to me, and the value from what my left subtree has returned to me. Now, since we are doing an iterative approach, these values too should have been stored somewhere. Again, I'm thinking, since this is a binary tree, I'm thinking of using another stack. So these return values would go into another stack. Okay. So when my write subtree is processed, basically what I would do is I would say my left subtree, the path would be equal to, so actually, okay, would be equal to this return values dot pop, and this would be, so for a very, very simple case where there was just a single node, right? And this particular single node, okay, it has no children. Then in that case, what I would get for my return values is, when we would actually get kind of zeros from those two. And then at this node, I would say, well, my diameter is actually 0, because because I'm just a single node. So here, so if my write subtree is processed, I would actually calculate this, and then I can just calculate my local diameter would be equal to actually the sum of these two. Okay. And once I have this local diameter, then what I can do is, number one, I have to calculate this longest path. So this longest path would be the maximum of whatever my longest path is. And whatever I have here, okay? And then I am going to push my result onto the stack. So I would actually append basically a value, and this value will be would be the max of, so this is the case where I'm returning back to my parents. So I'm going to choose the path that is longer of the two. I'm going to add one, and I'm going to return to the parent. So I'm going to max of this right subtree path, and this right and the left subtree path. Okay, I'm going to choose the maximum of that, and then I'm going to add one to it. So that's basically what I would be returning back to my parent. So that's what I have here. So if my write subtree was processed, then I would do that. Else, so this is another case where this is the first time I've just popped the root from the stack, right? The root node, and its write subtree has not been processed. So if its write subtree has not been processed, well, I'm going to simulate the kind of the call stack. So basically what I'm going to do is, to my post order, I'm going to append a tuple. And this time when I append the tuple, okay, I'm going to append this tuple, I would say root. I'm going to say true. Yes, this has been processed, but only after a couple of things. So what I want to do is I want to process them in a certain order. So left, right, and then myself. So here, if you're looking at as a stack, so I'm going to post order dot append. I'm going to say root, okay, dot right, comma false, and then post order dot append root dot left, comma false. So this is just kind of simulating like the call stack for a DFS, because we want to traverse left first. So that's what's happening here. So that's why we put left. Now let me make sure I got my tuples correctly lined up. So we've got my tuple, and this is the tuple. Okay. Now we also need, just like in the recursive approach, you need to have the base case. So here the base case would be if if you were, if you've actually gone past, if you're a leaf node. So in this case, you've gone past the leaf node. Then what I would do here is return underscore values dot append. I would append 0. So this is basically just kind of simulating the just the two things. One is a stack for these nodes, right? As they're being processed, and then also we want to keep track of these return values. So that's what's going on here. And we've got this, and then we are keeping track of this longest path. And then finally, I would like to return the longest underscore path. So I'd like to do a quick dry run, if that's okay, Gabriela, to just make sure
Yeah,
I don't have any
I
errors here.
just wanted to point you that the longest path, the last word and the return has a typo, and
Oh yes. Oh
let
yeah.
me see that.
Let me
And
check for the typos. Yes. Yes. Longest path is this one. Okay. This is just the stack here, starting with the root. These are the return values. Then I'm popping this. I get node. So the first time, okay, the right subtree has not been processed. So if right subtree has not been processed, then we are just going to put these nodes back on the stack in a certain order, so that when they get popped, they process. Okay, and finally, when we get to this, if it's being processed, then I can get my return values and then work with that. My right subtree path, left subtree path, calculate the diameter, update the longest path, and then push on the return values, the maximum of my right and my left, and +1. So okay, so that's
so what is it's one question, and when you are appending to the stack, you are appending first the root, then the right, and then the left. So why it should be in this order?
yes, that's a good question. So I could actually, I can explain it with a kind of like a dry run. So in this post order stack, initially, it's going to have root, and it's so I'll actually use these numbers here. For example, it'll have 1 and it'll have false. Okay.
Mhm.
So then
Right.
then what happens is this 1 and false will actually get popped from the stack, right? So this is gone now. And then, well, it was false. The write subtree was not being processed. So since we want to do a post order traversal, what we want to do is we want to get to my node last. I want to process my left first, then the right, and then my node. So that's why when I push it back on the stack, I'm going to put 1 and I'm going to put true. Okay. Then I'm going to put the next one I'm going to put is 3 and I'm going to put false because that has not been processed. Then I'm going to put 2 and I'm going to put false. So what this ensures is in the next iteration, when we pop the stack, because a list is like basically it's a last in, first out, right? So when you
Mhm.
pop the last in, first outs, and that's why we are using it for this DF, DFS here. So
Yeah. So
last in,
that's
first
the
out.
stack. Mhm.
So what happens is when we the next one to get processed will be this one. Okay, 2 false. Then the same thing will happen. Well, the right subtree has not been processed, correct? Because it was false. So then I'm going to now replace this one with, I'm going to now put, I'm going to say 2 and true, okay? And
Mhm.
then I'm going to push 5 and false. And then I'm going to push 4 and false. So this kind of so basically what has happened is we have actually gotten like right here now to this to number 4, and then here once we get to 4 and false, then again the same thing is going to happen. We're going to we will actually push 4 and true. And but in this case, now we have gone 4 is a leaf node. And so here we'll get, for the right is actually none. So it'll be none, correct? It'll be none and false. And then the left also will say none and false. So now we have
Mhm.
come past this. So the next time we pop, again, it's last in, first out. Now we have popped this one out. Well, it's not, it is none. So then my return values I'm going to append, will append 0. So basically this is now gone. Now the same thing will happen for the next one. I'm going to return values will be 0 again. But here now it will say, it'll get the node and say, oh yeah, right subtree has been processed. And so it will pop those 2 values. Now I should have also kept track of this one. So we have return underscore values, right? So return values is actually was 0, comma 0, right? Because those were appended to that. So now I come to 4 and it says, yes, my right tree has been processed. So it's going to pop this 0, right? And it's going to pop this one. And then my local diameter will be, well, in this case, it's just going to be 0 plus 0. So we are at this node. So longest path is currently just 0.
Mhm.
And then I'm going to append, well, in this case, maximum of 0 and 0 will be 0. So I'm just going to append 1. So now my result values will have this, will have 1. And so here, this one's going to say, this
The
particular
number
node,
2.
when
Uh-huh.
numbers being processed, it'll have 1. And then that's kind of how the flow will be.
Okay, so you will pop the number 2,
Mhm.
and
Yeah.
then you will go again of the question if the right subtree is processed, which is in this case, you will pop the 3
Uh-huh. Yes.
and
Yes.
1.
Yes. So actually here, just four has been processed. So the node that was processed was actually four. And
Mhm.
so four has returned. When four got processed, we got a value of one over here, right? Because this is just one
Yeah,
length of path.
just one.
And then the next one that's going to get processed is actually this other
The right.
child. Yes. So we are working on this one next. And so the same thing will happen again. So we'll come here, right? And they'll say, well, the right subtree has not been processed. Oh, sorry, yeah, sorry. It'll actually come here, and then it's going to change this, right? It'll say, okay, I'm going to put it as true, and let me actually push its right child and its left child. So it will be actually be none and false
And none
and none and
and
false. And the
false.
similar thing kind of unfolds. So I think the list structure lends itself beautifully to for doing this DFS, because it it's just like a last in first out
Yeah.
queue. And
And
so
that's actually what you are doing when you are using recursion.
yeah.
Only that in this way, you are using explicitly a stack, which is
Mhm.
implicitly used in the recursive solution, but it's in the backend or in the compiler, it's using also the stack, the call stack, and it's the same
Yeah.
flow.
Right.
Only
So
that you don't have to take care of the code when you are using recursion, but in this case, because of the iterative solution, that you can manage every detail in the code.
yes,
Very good.
that's right. Because yes, with the recursive solution, just because of the nature of recursion, the function, like the stack, is all taken care of for you behind the scenes, right?
Yeah,
But
but it
here we
also
have to
spends
actually
a
manage.
lot of the resources in memory
Mm-hmm.
because of every time it has to save all the state of the values of the variables,
Mm-hmm.
basically. So do you want to go over the time complexity and the space complexity?
Sure. So the time complexity is actually going to be, it will be on, because we have to visit every node. And as far as the space complexity goes, uh, at one point of time when you're like traversed, it actually depends on the kind of tree that you have, right? So it's the
Right.
same thing. If it's a balanced tree, right? Then the space complexity is actually going to be like O log n, because it actually depends on the height, how much how deep you have to traverse, versus a skewed tree. So a skewed tree, it would be O of n, because very similar, because we
Big,
are maintaining a stack here, a list, and so that many nodes would get added to it.
so you said big O of n or big O of log of n?
Yes. So it
In the
actually
case,
depends on
okay,
the
okay. Depending on if you have a balanced tree or if you have a skewed tree.
yes.
Like
Yeah.
the one that we have is skewed, right? Because it's not balanced, so it's more lean on the left
Mm-hmm.
subtree.
Mm-hmm.
So it's skewed. Okay, so this case it will be big of n, and that's the worst scenario when or yeah, when you have all the nodes in the stack.
Uh-huh. Yes, that's right. So like I was, the for the skewed tree, it would be like the case where they are all just like this. So you're just going, and all the nodes, this is like the worst case. They all around here. So you have all the end nodes. So you have a traverse all the way
All
down
of
to the
them.
last leaf node. And so basically, the stack will just keep building up, right? So you have these many elements.
Do you think of any other solution that you could use for this problem, and any other that you think could be good to try?
For
Like
this one,
instead of using a stack, or what if you could use a list instead of a stack or a queue? Do you think that those are also good solutions to try?
Yeah. So in this case, we are using a list because it best mimics the stack. So my choice of data structure was basically that I had to choose this is, since this is an iterative approach. I wanted to mimic the function call stack. And as far as trees go, they just lend themselves uh, to this kind of recursive kind of approach because you're basically repeating you're solving the same problem multiple times, right? So at each
Right,
node, I'm having to calculate the diameter at each node,
exactly.
and I need to
Mm-hmm.
look at the left and the right. So it's kind of like I'm kind of repeating the process at each node, and so
Yeah,
this
correct. Yeah,
approach.
you have to repeat the same processes on every node,
Yes,
basically.
yes. Even if it's the leaf node, the same thing's happening. Mhm.
Okay, Daniela. Okay, I think I don't have any other I don't have any other questions. Do you want to run the code or just to see if this is working
Sure. So,
with the,
oh,
okay,
there was a
here we go.
typo. Sorry.
Just missing a parenthesis.
Let's
Yeah,
see.
that's always happens. That always happens.
Let's see.
I think that you're missing again the same case
Oh, yes.
for the line that it's
Yes.
above that one.
There's a typo there.
What's the same? Okay, that's good. The indentation probably is not exactly the same. Because yep, don't worry about it. I think we can.
Oh, yes, I know. Well, yeah.
It seems to be like you have to align with the while at the.
Mhm. I also have maybe it's all right. So we have while, and let's see. Um, if else in one here, one here.
Mm-hmm. I think that should be
Okay,
the
return
indentation
the longest
longest.
path.
Mm-hmm.
Okay, and that should be an integer.
Mm-hmm.
Oops.
Yeah, I think that was the problem, and sometimes that happens with the lead code platform. Sometimes it takes some time to run.
Mm-hmm.
Okay, so that's okay. That doesn't it's not a problem. I think
Mm-hmm.
we can go with that. So yeah, so I think that's it for us for this problem.
Okay, so I'm just walking through the code again to look for typos. So if write subtree process, of course, we're going to do something else. We have to actually append this particular node. And I think before it was like I had a typo. I was pushing root, and that could cause us
Okay,
big
okay.
problems. So I changed that to
Understood.
node, and I like to fix this and see, and
Now we can run it.
from here.
Yeah, we
And
missed that typo. Um, I think there is another typo probably, or result
this,
values is return
yes. So
values.
we've got some typos going on here. So yes.
That's
So
okay.
return values. Make sure return values here, and
Mm-hmm.
the interpreter
Mm,
is doing its job.
yeah.
So we
So
did have some typos. So
that's okay.
let's the yes. So a couple of things to just note is to pay attention to these particular variables. Yeah, I missed that, and
No
also
worries.
this one. Okay. Well, thank you for pointing that out.
You're very welcome. That happens to all,
Okay.
like it's normal. That's
Okay.
okay. And I'm glad that you find it, that you found it.
Mhm.
And yeah, so it's accepted.
Okay,
Thank
thank
you,
you.
Daniela. It
Thank you.
was a great explanation and solution.
All right, thanks.
Thank you.
So welcome back for the second part of our mock interview. And for the second round, Daniela, will play the role of the interviewer, and Gabriela is going to be the interviewee. The problem that we're going to solve is lead code 797, all paths from source to target. So, hey Gabriela, how are you?
Hi, Daniela. I'm doing well. Looking forward to do the solution for this
Okay,
problem.
all right. So the problem that I have for you is all paths from source to target. Can you see my screen?
Yes, I do.
Okay.
I see the
So
lead code.
all right. So here's the problem. Given a directed acyclic graph of n nodes labeled from 0 to n minus 1, find all possible paths from node 0 to node n minus 1 and return them in any order. So the graph is given as follows. So in this case, there are actually 4 nodes. So this is from 0 to 3. The graph is given as follows. Graph I is a list of all nodes you can visit from node I. That is, there is a directed edge from node I to node graph ij. So here, basically, you have these pairs, okay? So you have a list of lists. So, so for at index 0, right? So from 0, I can go to 1, and from 0, I can actually go to 2. So these are the 2 nodes that I can reach directly. So I'm directly connected. 0 is directly connected to 1 and 2. Now, as far as 1 goes, 1 is can be 1. There is an edge. There is a directed edge, right, from 1 to 3. And then as far as 2 goes, there's a directed edge from 2 to 3. But as far as 3 goes, it's like a sink. There's no edges going out from it. Now, uh, basically the ask is that you list all the paths from 0 to 3. So you can go 0, 1, 3. You can go 0, 2, 3.
Very good.
And likewise, we have here, so there are actually 5 nodes from 0, 1, 2, 3, 4. And as you can see, they're basically listing all the edges
The
going
edges.
out from 0. So there'll be 4, 3, 1, and that's what you got. And basically, the ask is give us all the paths from that you can take to get from 0 to 4. And
Yeah.
so here's the
So all of
output:
them,
0 to
all
4.
possible paths.
0, 3, 4, 0, 1, 3, 4. Yes, all the possible paths. Yes.
Very good. And we
And then
have
you have some
some other
constraints.
examples and constraints.
Where
Where n is
they are
the
unique. All the elements of graph I are unique. And the input graph is guaranteed to be a directed acyclic graph.
Very good. Okay.
Acyclic graph. Yes.
Acyclic graph. Very good. That's very important to mention.
Mhm.
And also the length of the graph is equals to n, which is the number of
Yes.
nodes that we have, and which could be between 2 and 15 inclusive. And then we have the connections can be, of course, all the connections are in the are of nodes that exist in the graph, right? So all the nodes are connected. Very good. Okay, Daniela, I think that explains what is the problem. So I think I can start sharing, so I can give you
Sure.
the explanation of the solution.
Go
So
ahead.
let's
I can
start
stop
with
sharing.
that. And I'm going to share my screen, and please let me know if you see my the browser should be. the one that is sharing. Is it? Okay.
Yes.
So we went over the what is the description of the problem, and there is something very important in this problem, which is that the graph is acyclic and directed, because we have graphs that are cyclic or that can have cycles between the nodes, which can be a problem when you are exploring a graph, because you can go into an infinitive loop if you run into these cycles. So we have an acyclic graph, which we don't have to we don't have to be concerned about infinite loops. And it's also a directed graph, which means that every node is connected to another one with just in one direction. There are no both directions connections. And so that's also, which makes a little simpler this problem. So let's try to do one example just to clarify what is the structure of the problem. So I would like just to draw a little graph with like the one that we have already. Perhaps could be just want to go over some of the details that we have here for the problem. And I'm going to use also four nodes in this graph, and every node I just want to go over how they are connected. So let's say that we have just like the problem is describing, we have 4 nodes, and what we want is to find all the paths that can go from my starting node. So the start node is always the number 1, and the goal node, it's the number n. In this case, it's in this case, if we start with the 1, we have 1, 2, 3, and 4, and that's basically the kind of problem that we have. So if I want to connect between, if I have one connection between the 1, the 2, let's say that we have this. I'm going to switch to the arrow so we can. Okay, so we can put also the direction of the path or the connection. Can say 1 is connected to the number 2, and I have connection from 3 to 2, and I have one connection from the 2 to 4, and then I have one connection from 3 to 4. Okay, so we can have this kind of graph, and this one it's a graph valid. So I have, like I said, we have 2 things. We have the starting node, which is the node number 1.
Yeah. So Gabriela, I'll just mention that our start node is always going to start with, we're going to start with 0.
Okay, that's a good.
And
so we can say that the start node is going to be always index base 0, and in this case, if we have
3.
If we have 4, it will be 3.
So we can just replace 4 with 0, or whatever you want to do.
I think it will be better to replace all of them.
Okay, sounds good.
Just because we don't want to get confused with the numbers. And so the start node is the 0, and the goal node is it's 3. So that's the same to say like the goal node is n minus 1, because the number of nodes is n. So this is 4, and the goal node is 3, right? Okay, so these are my nodes, and one thing that it's also interesting to see is how I need to read the input so that I can know what are the connections between the nodes. And we have, like you said, we have a list of connections or the edges in the graph. And I want to just put this example. For example, for 0, we have, I'm going to put another text here. For the 0 node, I have 2, I have one direction or one edge that connects with the node 1, and then I can go to the node 3, which that could be a valid path. And so I'm going to just put the connections between from the node number 0. So from the node number 0, it's the 1, and then I have a connection with the 2. Just those 2 connections or neighbors. And then if I want to put the connections in the number and the node number 1, I have just one connection with the node 3, right? And then if I go to the node number 2, I have one connection with 1 and then one with 3, right? And the last one, which is the node 3, doesn't have any connection with any other node. Okay, so this is like this is my input for this graph. And what we want to do is going over all the possible paths that we can use in this graph to go from the, like we said, the start node 0 to the goal node 3. So for example, in this case, we can have from a valid path could be from starting node 0, then the 1, and then we go to the node number 3. So that could be one possible path. Or we can use from the starting node 0, we can go to the node number 2, and then we can go to the number 3, and we are in the goal node. And I think we don't have any other. Okay, no, sorry, I have one more, which is starting with again with the number 0, and then we go to the number 2, and then we can go to number 1, and then we can go to number 3, and that's the final, or the target in this case. Okay, so I think that are all the possible paths that we have in this graph. And since we are talking about exploring all the possible paths that we have in this graph from one source node to a target node, which are the starting is 0, and then the goal node is the number n-1. So we're talking about exploration or methods to explore a graph, where we can traverse through all the nodes and looking for the paths that we want, which are valid from the 0 to the 3 node. So for that, there are a couple of solutions that we can use. And there are two techniques that I would like to mention, because I think both are very useful techniques. And one is the breadth first approach, breadth first traversing, or BFS. Yeah, it's breadth first solution. Or we can use the deep first approach. And both of them are ways to explore a graph. In the first case, in the breadth first solution, we are exploring we explore every node, and we go over all the connection that this node has. Like I did, just like I did, I went to every node, and I was going over all the connections that this node has, which is a little different if we use the deep first connect, the DFS solution, because in the depth first, what we do when we are traversing the graph is we start with a node and we go until we finish this path. So if I start with the 0, I am going to go over just one connection, just so 0 to 2 to 3, and then I need to go back in the same path that I traversed to discover what are all other possible paths that this node has. So I need to like return in the same path that I went on. I go back, and then I explore another path. So it's a different way of exploring a graph, and both are valid solutions for this particular problem, because what we want is to explore the graph and explore all the possible paths. But what I want to use in this case is just the breadth first solution. And I want to also mention that this one is using a queue, which is a structure that allows you to push the elements in the queue or the nodes. And what you do is like the first that enters in the first in is the last one that is out. So because it's a queue. So that's the principle of how a queue it's working. And if we were using a stack, we were doing first in, last. Sorry, I think I confused.
Yeah.
The
Yes.
first in is
The first in,
first
first
out.
out, yes, will
Yeah,
be the queue.
just was
Okay, so
just
Gabriela, if I
clarifying.
may ask, in the
Yeah.
interest of time, can you just walk us through just your algorithm and just kind of just share how you would come up with the result? You can pick either one of the traversal, and I think you mentioned breadth first is what you would like to choose.
Yeah,
So if you could just talk us through. Uh,
of course. Yeah, I would like to go to the lead code,
sure.
to the lead code page, so we can, just write the code and just see what the solution is going to be looking like. So I'm going to use C#. That's my the language that I want to use. So it's a list of lists. So we are going to return a list of lists of all the possible paths. So what we want is just first we want to declare a list, like the what is what. This is what we need. The first thing that we need is our queue, and then we have to return the a list of lists, which is the result. So I'm going to declare a list, and I am yeah, so I'm going to write that. Actually, I'm going to copy this. So it's the same. It's the same type. It's an integer, and I'm going to just declaring the list of integers. Okay, because that's the type that we have in the input. And what the first thing that we need to check is that is our graph having, it's a graph with does the graph have nodes? So I'm going to check just if I don't have to go over a loop where if I have an empty graph with no nodes. So I'm going to just double check that my, oh, sorry, that the length is not, if it's equals to 0, then I'm not going to traverse this graph, okay? Because there are no nodes to traverse. So I'm going to return my my list that I declare because it's empty and there are no nodes in this graph. And then what I want to declare is my queue. And I want to have in my queue all the possible paths that I have discovered so far as I am traversing the queue, or sorry, the graph. And so I am going to just declare my list, my queue, and that it's going to be saving us the list that we are traversing. And I want to also have just my current path, the one that I am currently exploring. So I have a current path, and this is just a simple list, just one particular path, and it's empty. And so we say that we have two things. We have the goal node, which is equals to, let's say that we have this, this is my goal node, and this is the graph length -1, right? That's That's a constraint that we have. And then I'm going to have my starting node, which is I, and it's going to be always 0. And after that, we want to start always with the node 0, because that's always our like the starting point in any case. So I am going to have in my current path, I'm going to add to my current path the node 0. That's a constant thing. And then what I want, the breadth first approach is always starting with the first node that I am starting to explore the graph is the one that is going to be included in my queue. So that's also the first thing that I am going to initialize my queue. And that's my current path. That's what I have in my current path. And then what I want to do, it's starting traversing the graph, because now I am positioned in the node number 0, which is starting, and then I want to start exploring. And then, so I am going to do a while for that. And as long as my queue has more nodes to explore, then I'm going to keep in the loop. Okay, and what I want is I have my starting point. So from the queue, I'm going to take that node, and so I'm going to do at the queue. So my current path, because I am exploring the path, all the possible paths, I'm going to take from the queue what is the one that I want to explore first. And so that's the current path that we're going to take from my queue. So I'm going to the queue. Okay. And the first thing that I want to check, if I have a path, I want to know if if I had reached the goal node. So I'm going to check if my current path has, because we have a queue then, or a list, we have to know if the last node that I have in that list is my goal node. So if it's equal to n, that's the one that we have. So in that case, this path, this current path, can be part of my result. So I'm going to add that to the queue. Okay. And then if this is not the case, then that means that I have to keep traversing the graph to find what are the possible ways or paths that I can traverse in this graph. So this variable is going to always have the last node that I have in my current path, so that I know what is the next node that I'm going. What is my next path going? So that's what I want to take from my current path to make that connection. And then from there, I'm going to going over the neighborhoods, which is what we have in these little arrays. So I'm going to take that connection, and I'm going to look for their neighborhoods, for their neighbors. So I'm going to declare just a counter, and I'm going to start with the index 0, because we have an array. So we are going to always have to start with the 0, and we're going to, since this is the input is an array, so this node is the last that I took. So that's the one that it's my index in this input. So that's the one that I'm going to be using to get all the connections. And so that's the index that I am iterating over. And I'm going to increment this counter or this index. And let's, what we want to do is we want to add to my queue those connections that I have in this node. So for that, I'm going to use a new variable, because this is the path that I am traversing. So I'm going to put the name of new path in this case, and I'm going to, again, it's a list as the current path, and I want to keep the nodes that I have already traversed, because those are the ones that I have done in my breadth first my breadth first algorithm. I always want to take all the nodes that I have traversed, and then I want to go to the next nodes, but always keeping the ones that I have already visited. So that new path, I'm going to add the one that I have in this iteration, in this loop, and I have this array that in index k, and then I'm going to, because that I have in my path, I'm going to also enqueue that to keep that in my queue and going over all the different paths. So my queue is keeping the track of all the possible paths that I have traversed, that I have visited, so that I know where I'm going to go next. And after that, when we finish this while, we're going to have, because we have this check that if I reach to the, if I went over all the nodes, or if I visit the node that I want to be as the goal, in that case, I am adding to the result. So the result at this point has all the possible paths, and that's the one I am going to return. That will be the one that has all my possible paths, that includes the goal node. And that would be the BFS approach in this case. So I am going to just going in with the time complexity. And in this case, we have a regular graph, and we know that we have to visit all the nodes in order to get to the path that we want to reach. So if that was the case, if that is the case, then the time complexity is big O of the number of nodes that I have in this graph. But we are not doing just that. We are traversing also all the possible nodes, or the connection that each node has. So that's another variable that we are doing. So that's n. So let's say that we have n nodes, and also because of all the possible connection that each node can have, it's n. So we are going to have big O of n, and I'm going to have by n connections. So that's one. That is one. That's the time complexity that I'm going to use for traversing in the worst case scenario. And so this will be n power of 2, because we have n squared. In this case, this is the time complexity in the worst case scenario. And after that, also, we want to know what is my space complexity. So the number of nodes that I have in the queue, or how long is the queue at the maximum value, it's again the number of nodes and the number of connection that each node has, which is the maximum. It's n, so it's again n squared. So that's the maximum time, and that's the maximum space that we would take with this approach. So I guess we can just double check that we don't have any typos or problems with the syntax. And let's see this count. I think it's fine.
Gabriela, on line number 6,
Line
is
number
that
6.
graph.length?
I think
LENG.
there is a typo, right? TH. Thank you. That's always something that I get confused. Okay, so that's the length. Here is fine. Graph.length is -1. And thank you. It's also fine. And I think I don't see any other typo. I guess we can.
At line number 30, you add the current path to the result because we have got to the final node. And then do you reset the current path, or is it, how is that set?
Yeah, every time that with the queue
Oh, but
a
okay.
path,
That will be updated.
it's like the reset.
Okay, got
Yeah.
it.
Yeah, that's important. I'm glad that you asked, because sometimes it could be like, when is this happening? Like, yeah, so every time we assign the current path with the one that we are taking from the queue. And so I think we can try with the example that it's this case that we have in the and okay, I think I have probably I'm missing valid term. I guess int supposed to be int, but I have a list of integers and term int. So let me check. I think I have.
Is there an extra like a bracket after the int?
Yeah,
I
I
see
think. Yeah, I think
towards
so.
the end.
Yeah, I
I'm trying
think.
to match it.
Yeah, I think that was it. Yeah, we have. This is the type.
This one.
And
This
that's,
1,
yeah,
2, 1,
I
2.
think
Okay.
this is okay now.
All right. 1, 2.
Yeah, this is closing, and yeah,
Okay.
I think that's, yeah, I think now it's fine, right?
Okay.
Thank you. Okay, we have another one, and to bool. Okay, so it's k should be mine less than the length. Okay, so I was missing this k. Okay, and I think that would be, okay. So this is working for this case. So we can submit, and we'll see if this is correct. Okay, so this is fine. The solution is fine, and it's okay. So this is the way to do it with breadth first search.
All right. Okay. Well, thank you, Gabriela, for going over your solution. It was very clear that you were using breadth first search and you used the DQ. So thank you for sharing your solution.
Thank you, Daniela. Thanks to you for also helping me to find the typos.
That's all right. Okay. So with that, Gabriela, if you could just